Okay, we're going to look in this video at integration by inspection again, and we're going to look in particular at this wee result that we have. So this was if you differentiate ln of f of x, you get f dash of x over f of x. That means if you're integrating f dash of x over f of x, you'll get ln of modulus of f of x. And we mentioned before the modulus is because ln is only defined, or logs are only defined for a positive value. So we're going to jump to examples. Here is the first one is a very easy one, and we've already talked about these standard results. So this is just going to be integrate 1 over x, you get ln of modulus of x and then plus c. Okay, so every time in this, just have we look and just check this one out. We've got f of x on the bottom line, so if you which is just in this case is x. If you differentiate x, you get 1, so it's in the form that we want. Okay, in this one, have a look at it and think, what do you get when you differentiate the bottom line? If you differentiate the bottom line, x plus 3 differentiated gives you just 1. So you're actually in this form, f dash of x over f of x. So here, when you integrate, all you're going to get is ln of modulus of x plus 3. And you do need the modulus. And then remember your constant of integration, c. Okay, if we go on down, and our example 3. So example 3, we've got x over x squared plus 1, and that's what we're trying to integrate. Now the problem with this one, it is not quite in the form where you've got f dash of x over your f of x. Now why that is, if you think about it, you've got x squared on the bottom line plus 1, x squared plus 1. If you differentiate x squared plus 1, you get 2x, not x. So what I'm going to do here is I'm just going to rewrite my example 3 so that it is in the form that we want. So my example 3, I'm going to change it so that it becomes a half upon 2x over x squared plus 1 integrated with respect to x. It's now in the form that we want. So the integral part just becomes ln of x squared plus 1. Notice I haven't used the modulus sign because there's no need. And then we have a half out in front of it as well. And that's it done. So a very good wee trick. So let's just look at what we've done here. It wasn't quite in the form f dash of x over f of x. So just force it to be in that form. And then you have to adjust the constant outside so that this line is still the same as this line. Okay, example 4. Okay, again, if you differentiated this bottom line, you would get a 3. So it really should have been a 3 up on the top line. So I'm just going to force it to be that. So I'm going to put a 3 up top, and then I've got my 3x plus 5 on the bottom, and that's my integral sign. So that's clearly not the same thing, but if I put a third in front, then that is the same. So now we're good to integrate. We've got a third upon ln of modulus 3x plus 5, and then plus your constant of integration, c. Okay, this is just to show one with limits on it, so a definite integral. Differentiate your bottom line, you'll get 2x plus 3, and happy days, that is what we've got on our top line. So we're good to go, we're all ready to integrate. Integrating, we now use square brackets, and it's going to be ln of modulus is required, x squared plus 3x minus 1, and that's between 1 and 0. So first square bracket is going to be ln of modulus. 1 squared plus 3 times 1 minus 1 is going to be 1 plus 3, which is 4, minus 1, which is just 3. And then minus, good example here because it shows you why the ln is important. It's going to be ln of 0 squared plus 3 times 0, then minus 1. So that's just going to be modulus of minus 1. So that shows you why the modulus is important. So get rid of the modulus, that's just ln of 3 now minus ln of 1, and if you do that in your calculator, ln of 1, by the way, is just 0, so that really the exact perfect value is just ln 3, and that's it done. Okay, we've quite possibly seen this one already, but just to show you, use doing this one again, so we'll write that as sine of x over cos of x, and then you can see again, it's not quite in the form we want, differentiate cos, you get minus sine. And take a minus outside to make it all right. So that's now minus of ln of modulus of cos x. And then that's just going to be ln. The minus can come up, and that's going to be modulus of cos x now to the power of minus 1. And the cos to the power of minus 1 is sec. So it's ln of sec x plus c. So again, a very common one that they like in exams. So that's why we're just showing that one again. Okay, last example. Before we do anything else, I'm just going to show you a nice way of doing these questions quite often. Is just say I is equal to. So that's like your integral is equal to. And you'll see in this question, it just makes it easier for us to refer to it later on. Now what we've got to do first of all here is divide through by the divide because the order of the top line is greater than or equal to the order of the bottom line. So you've got to do your x, and it's got to get divided by x minus 4. So x goes in the x one time, and write down x minus 4, and then subtract 0. So here we are, 0 minus minus 4 is going to be just positive 4, and x minus x is going to be 0. So therefore, your integral in this case just becomes 1 plus 4 over x minus 4. And if you integrate 1, you'll just get x. And integrate your 4 over x minus 4 is going to just be 4 times ln of modulus x minus 4, and plus your constant of integration c. Okay, that is us ready to do topic 7, integration b, and it's exercise 2.